Okay, we're recording now.
Okay. All right. Again, I want to thank everybody for the hard work that they've done. We'll ask you to introduce yourself briefly so that we can know who we're looking. We've not seen your pictures on the other side, so go ahead. Martin, go ahead, you start.
Yeah. Well, I'm Martin Delcourt, UMOS team lead, and we have been working on the Drillbotics project since the beginning of the year. It's the first year that University of Mons participates to this this amazing project, and we are happy to be here today because it was a lot of work, and now it's the judgment day, and I hope that all our efforts that we have brought to this project will be rewarded by a successful drilling process. So thank you to be here first. And yeah, thank you.
Next.
Hello, I'm Remy Destrubec. I'm a human student, and in this project I work on the mechanical part, and I was the other manager.
Hello, my name is Anthony. I am a student in the University of Mons. I worked on the mechanical part, and in particular in designing and dimensioning the rig. So, I did a lot of CAO of the rig, and so.
Okay.
Hello, I'm Julien. I'm a French student, and I'm in the UMOS for the Erasmus semester. So I joined the team only in February, and I work on the mechanical part, and I was the secretary of the team.
Very good. Anybody there from TUC would like to talk?
Yes, so hello, my name is Haran Ambosalimitsidis, and I'm the team lead of this year's robotics team, and it's my second year participating in this competition. And yeah, what can I say? We're excited to drill. And I think I speak for the team when I say we worked as hard as never before, and we want to show what we did. And I think my team members can introduce themselves. Yeah.
Right, so my name is Kanan Al-Masrani. I studying mechanical engineering at the TU Clausthal, just about to write my bachelor thesis. I'm participating for my first year at this competition, and I was in charge of the mechanical and manufacturing aspects of our rig, and particularly redesigning the VHA and optimizing it, and the constructing a new steering mechanism. Excellent.
Hello everyone, my name is Ali. I'm a student, Bachelor of Petroleum Engineering. My role in this team is more like a support and administrative. Yeah, really happy that we're here. And my colleague.
Yeah, hello everyone. My name is Farouk. I've been this team since the past 4 months. I've been responsible for designing the GUIs, interfaces, working with data, programming some stuff also. I've never been in Belgium or in this competition, but I'm excited.
Very good. Can somebody use their phone or this camera as required and move over to one of the rigs? Let's start with you, Mons. If you'll show us your rig and kind of give us a little bit of a description. And for the judges, as they go through that, if you have any questions, don't hesitate to ask. So show us what you got. Tell us about it.
So, hello everybody. Better.
we will show you our rig. So we have the structure, it's in steel. Then we have here the rock. We use a back for, we're using the water. We work with all the time with the save water. We do this for saving the planet, and water is important for us. So we don't want to waste it. So we reuse it with a pump that we can adjust how much water we put for the forage. Just here we have the steam train with the tool. DDS, an enterprise in Belgium, in Charleroi, next our university. And here we have the swivel for putting water in the rig. Here we have the motor. We use a servo motor. Then we have the reductor, gearbox there, and so it's the swing train for adjusting and go up or go down. We have screwball, just that we have. We did all the design of the screwball, and on the screwball we have also our servo motor. We have two servo motor. So with the servo motor we can have all the information. So the torque, speed of the tool, and other things. Then we have
You're good. We can see you.
we have here the electrical ports, so we can go up, go down, go in manual or in automatic. We can drill. We can drill. We have the pump. We have a stop button, and we have the reset. We have configuration. Until we can use the endpoint. Yeah, on. Well, yeah, for the design of the display, we have very different inspired by there are several types of components with hardware and software components in the display. So we can control it. We can control the lighting directly again in the test that will give us a lot of information and concerns all from the stats and characterize the delivery process. And we have taken some various characteristic values between the mark and the fields. That permits us to optimize the regulation loop, which is PI this sheet. We can see here that we have chosen to use one
Hey, Martin, it's hard to hear you.
Excuse me.
Yeah, you're a long way from the microphone, so
Yeah. Maybe take the sheet to the microphone.
Do I need to repeat a lot of things? What didn't you understand?
yeah. You did. What is on that sheet? We couldn't hear you.
So on the sheet, you will find some characteristic values that we have taken from a precedent drilling process. And so we have the characteristic between the RP and the weight and bits. So we can see that to stay in a safety area, not to be unstable with the pipe. We will reset the ARP at 15 millimeters per minute. And we can see here that this is the interval where we will work, and the PI regulation will try to command a precise weight on bits. So with this weight on bits, we will control the weight of bit by regulating the ARP. That's the way it works. And this for a rotation speed of the bits of 120 RPM. So we have chosen this this speed because the PDC, the bits, have been glued and not melted on the bits. So we cannot rotate it too much fast.
Okay.
Martin, question. So you're holding RPM constant, but you're changing weight on bit to target the optimal ROP?
Yes, yes. So the rotation speed is constant, and we control. We are looking for a precise weight on bit by controlling the RP. That's the way it works. That's the way the regulation loop works.
Okay, so it's an ROP control. Okay. And how did you define instability? Or how did you find that region?
We found that region by empirical tests. So we have tested the bit, and with the pipe that we have, which is quite thin, we have increased the RP until it's almost failed. So of course we stood in a safety zone. So we calculated some extreme values that we always stay behind. We take care of the safety, of course, of the user, but also of the motors that are present in the train. And with this experimentation, we have chosen this region to stay. We could go faster, but we want to stay in a safety zone. So we don't want to go too much fast and to have problems.
Okay.
We play safety today.
I see that there's a red button on the front of the panel and a red switch on the side. What do they do?
And the red button, and what else?
There's a red switch on the side of the panel.
So there is the red button, and
yes, and that when you push that button, what happens?
So it's the emergency button. So if you push it, the drilling motor stops, but and the hoisting system stops, but you're able to move the table. You're still able to move the hoisting system, so you can take your bit out of the rock. And this has been programmed in the PLC software.
Okay, and does it disconnect the power?
It disconnects the power of the motor, but not of the drive. So we, since there we can program the way we want the emergency button to work. So we want it to work. We wanted to we wanted still to be able to control the positioning, the position of the bit, but not to be able to drill anymore.
Okay. And then on the side of the panel, it's a switch. Is that a power switch?
This switch.
No, on the other side. Yeah, right there.
Yeah, this one. On the side of the electrical cabinet.
Yeah. Does that disconnect power?
Yes, this is the switch to the switch for the power at the input of the electrical box. So it is 400 volts, three-phased.
All right. Yeah, because the button on the front is not going to protect you from an electrical shock. So you'll have to, if you had some electrical problem, the only place to turn it off is on the side of the box, not the front.
Yes, of course. If we are still able to move the table, we can have an electrical shock. But the system has been sized for the safety of the user next to the rig and not next to the electrical cabinets.
Okay, and then from a if you have a ground fault,
yeah,
is there a ground fault interrupter?
We have all kind of software and hardware protection. If you can see inside the electrical cabinet, you will see particularly some magnetothermal protection to the drives, to the motor and the pump drives.
Okay.
Otherwise, there are some all kind of protection.
Okay, and are those PLCs on the far right?
Excuse me?
Are those PLCs on the right-hand side?
On the right side. So these are the drives that control the motors. This is the drive that control the pump. And beyond that, I don't know what you mean.
Do you use a programmable logic controller, or do you just control it with the left?
We run it with a PLC software.
Okay, and the PLC software, where's the PLC itself?
The PLC is the software, so we use Codesys software to program the drives.
Okay.
So where is your algorithm running, your ROP control?
Can you repeat, please?
The control algorithm for controlling the ROP and controlling the weight on bit, where is that running? In the PLC, or you have a laptop or something that's connected to it?
Well, we can control it from our laptop, but we have a PLC, so we are not obligated to connect our laptop to control the rig. So the rig can the system is made that you can control the rig only by using the display on the front of the electrical cabinet.
Okay.
Okay. Good.
Is there any ability? So a lot of the rigs now are moving to a remote control system, right? Where you can control multiple rigs from a centralized location. Did you look at any ability to control this from a separate location, or is everything has to be controlled through this panel?
We are able to control from a different side. We can connect with our computer with the proper material that we have, but we haven't installed it yet. But we could do that, yes.
Sure. Okay.
Martin, can you talk about the BHA itself? What does the steering unit look like, the sensors?
Well, I remember that it is the first year that we participate, and we haven't had the time yet to create the steering system. Okay, so it's a straight drilling process. Yeah, and about the sensors, we have chosen to use servo type motors in the purpose to collect output information from these motors. And this information will give us an indication of the torque and the rotation speed. For the hoisting system, we use the rotation speed of the motor to control the speed of the table that will go up or down, and the torque of this motor to know what is the weight on it. Concerning the drilling motor, the rotation speed is direct information that have been integrated to have a curve that is that we can read on the display. But we collect all information from these motors, and the torque of the drilling motor is also a direct information from the motor.
A question, you mentioned torque is a direct measurement. So you have strain gauge, or you're measuring it from the current and then calculating the torque?
The servo motor works in the way that we collect all this information with the voltage and the current that goes through it. Well, of course, obviously, it's a bit more complex than this, but yes, typically yes.
Okay. What about any downhole sensor?
Wait
do
a
you know
second,
where
Joshua,
you are,
just a
like
second.
inclination?
Just a second.
Yeah.
On the torque measurement, is that coming from the servo motor and then you're calculating torque, or are you getting torque from the drive? So are you measuring the current and voltage at the servo motor and calculating torque, or are you getting an output from the drive itself that gives you a torque output?
It's the drive that controls the motor by collecting information, and we read these informations on the drive.
Okay, got it. Thank you. Go ahead,
Do you have
Shashi.
any? Yeah, no worries, Fred. Do you have any sensors in the BHA to measure inclination or azimuth or the position of the bit?
No, in all the sensors are we don't have sensors on the bit on the BHA. All the information that we collect from the drilling process is from the motors.
Got it.
That's the reason why we have chosen to use servo motors, to have some programmation advantages of its simplicity.
Can you, one more question, can you talk about the hydraulic loop? So how is the fluid going to the bit?
Yeah, so for the fluid, we use a flow regulated pump. So the pump drives the water through the system. It goes in the pipe, and the wastewater go up in the hole, fall in the recipe in the batch, and there is a filter that we collect. We collect the wastewater with a filter, so there is no there is not dirt that goes in the pipe and go back in the process.
Can you show us the filter?
Yeah, please, can you do that to me?
Okay. All right, thanks.
I have no other questions. This looks good, team, for the first year. Looking forward to getting this thing running and see how it drills.
Hey,
I'll
real
pass it
quick,
on to the other judges.
real quick. You said you don't have any sensors down in the BHA, magnetometers, accelerometers. How are you getting your survey position as you're drilling?
By using the ball screw. By using the ball screw, because if you couple the ball screw with a known rotation speed and controllable rotation speed of the servo motor, you will be able to control the position of the bits inside the rock. However, you have an error factor, because the pipe is flexible, and maybe we lose several millimeters by the bend of the pipe.
Right.
But it's not controllable for us to. We can't know what is this loss of distance.
Okay, and then what's the survey frequency? I guess survey quote unquote frequency that you're like that you're taking. So how is it by the millimeter? Is it by the second? What's your positional survey frequency? I guess I would say.
Well, we take information real time. I need to check the documentation of the drives. I don't know it.
Probably every couple seconds or something.
No, it's faster than this.
Okay, cool.
Regarding the twisting and the drill pipe, you mentioned that you use a titanium alloy to overcome the twisting problem of the drill pipe. Are you still using that one, or did you change the drill pipe material, or what kind of adjustments do you make to prevent that?
We have we have sized forces that are going to be applied on the bit, and we went with a standardized with a standard of the pipe. The pipe has dimensions. We began with standardized dimensions, and then we have calculated forces like the torque or the weight on bits that is going to be applied on the bits, and we don't we haven't yet changed the material of the pipe, but what we have put it limits on the software not to have these kind of problems.
Got it. Thanks. Regarding that testing that you made, to check the motor conditions, how do you measure the vertical and horizontal force? Can you walk us through that test?
What kind of information do you want to have?
How do you actually measure the vertical forces and the horizontal forces on the motor when you estimated the parameters?
The parameters to implement in the software.
Yes. Yeah, you mentioned that there is an efficiency region of 450 to 500 newtons, and okay. You also have the horizontal and vertical forces in there, and I just wanted to make sure I knew how you actually measure those forces.
Okay, so what we did is that we have made some tests on another bench test. We have calculated forces that were applied on the cutter. Then we have put it a high security factor to be sure that the speed of the test wouldn't be a problem. A problem of converting these values from a low speed test to a high speed test, which is the drilling process that we have here. And we have converted these results with the geometry of the bits that that BBS made for us, and with this we were able to know what were the function of the ROP. We were able to know about what torque we would have and what weight on bits we would have. So.
Okay. Thanks. So it was another test bench.
For this part, it wasn't empirical. It wasn't from experience. It was from external experimental tests that have been made previously.
Thanks. Yeah, that actually caught my attention because I think you were one of the first teams that actually did experimentation to get your results instead of just theory. That's awesome, and congratulations for a first year to rig. This is incredible.
Thank you very much.
I've got a couple of safety questions for you. I see that you have perspex or plexiglass shield around the rock, but I don't see anything that's going to protect you from this if something breaks that's spinning. So near the top drive, near the drive motor, if one of those fittings comes apart, it becomes a projectile. Is there anything that's going to keep that from flying around the room?
Concerning the plexiglass plates, well, we have put the plexiglass plates for the bird projections and the water or wasted water projections. And with the pump flow that we are able to provide, it won't be a problem for this this kind of projectile of projection. Beyond this, of course, we have that's kind of a bit, comment on dit en anglais? Excuse me. Goggles. Okay, sorry. So for the user, we have goggles. So that we don't have on us right now, but we will use them for our safety, which is the priority, of course, with the use of that kind of experimental machine.
Okay, but I'm more concerned about something that breaks and hits you like a bullet.
Yeah,
I'm just saying that you need to extend the plexiglass into the derrick as well as above, just around the rock. So yeah, as you make improvements for next year, you need to enclose the derrick in some kind of shield. It can, it should be removable, of course, but you should have something there for safety.
Actually, the protections are in the software. We have limited.
No, if something breaks, it's a bullet, and the software can't respond fast enough. We've seen it happen.
Oh, okay.
Okay.
Oh, it's noted. Thank you.
Okay. The other thing is in your hoist mechanism, there's a drive screw, and as you rig up and rig down, there's a lot of weight that's being held there, and you probably need either a pin or a bolt or something that you can put in that and lock that carriage into the frame, so that while you're working on something, if you're working on that drive screw, that piece can fall down and cut your hand off. So look at those safety items. What can bite you? What can hurt you? What can cut you? What can shock you? You need to do a very thorough safety review and say, what are the risks? And then you want to find ways to eliminate those threats. Okay, so as you go forward, you're in year one, right? But as you go forward, you want to make sure that this is completely safe. Somebody's going to be using this for this next several years to do Drillbotics work or research in your own lab, and you want to make this, it's going to be safe for everybody.
Of course.
Okay.
Yeah, thank you.
All right. Any other questions from judges? Any comments from judges?
This looks good. Maybe we move on to the next team, Fred.
I want to mention one more thing. Is it looks like you're using a brass tubing fitting, and if you look at some of the previous work, and I'll try to give you a reference, but they're not made for rotation. When most of those fittings are made just for hydraulic coupling, and they're not usually made for rotation. There are some fittings that will handle rotation. And so if you start building much torque, it's going to fail there.
Okay.
And I'm saying this because this is what happened in the first couple of years. Okay. And,
okay.
And so it's just buying the right fitting will make a big difference as you move forward. And then I wanted to, what is your maximum RPM?
120 RPM.
Okay. All right. That may not be enough, because the way that a bit cuts, it's a combination of how much weight pushes down into the rock and how many times it turns per minute. And you can't, and with this very flimsy pipe, you can't put much weight there on purpose.
Okay.
So you may need higher RPMs as you go forward.
Actually, the motors are not the issue here. We are limited by the assembling of the bits. So we could increase the rotation speed to 900 RPM.
Oh, okay. All right. Yeah, that's more like it. But we will talk with you and email you later with some comments.
Yeah,
that
sure.
like we're talking about now, that the team can use next year to improve this a little bit. I'm telling you, for a first time, this is outstanding. We've seen teams come in the first time and they've not built anything like this. This is really good.
Thank you. I appreciate it.
There's one more thing. If you win one of these contests, we ship your rig, but the way you've built it, it costs us too much to ship it. It doesn't fold up. Okay.
Yeah, we designed it to be as lightweight as possible.
Yeah, but I want you to. There's a question in the guidelines about how you calculate the shipping weight, and it's a combination of weight and volume. Yep. So you have no weight there, but the volume will still make this very expensive to ship, and it might not survive shipping. Okay, it might be damaged in shipping. So you need to consider that. Who knows? Next year you may be taking yours to Germany instead of what we're doing today, and so look at what you can fold up and put in the back of a van or a truck.
Okay.
Okay, good.
Yeah.
Listen, I'm giving you these comments because we've seen this since 2015, right? We got lots of years of people making mistakes. You don't have benefit of all of this hindsight. So again, I'm really impressed with what you've built. but I still want to help you make the next one better.
Yeah. And thank you for your advices.
Okay.
Maybe one more question.
Yeah,
Looks
sure.
like you've drilled 3 holes. Are those pilot holes?
Yeah.
Okay.
Sorry, can you repeat the question, please?
Yeah, I see 3 holes pre-drilled in the block.
Yeah.
Are those pilot holes, or you were testing your system?
We were testing the system, of course, but we are drilling straight, so they are not supposed to cross. The holes are not supposed to cross them.
Got it.
Themselves.
Have you looked inside the hole? Is it smooth or is it spiral?
You can see. Wait a minute. Maybe.
Yep. Pretty smooth.
Yeah, they look smooth.
Very smooth. That's good.
We only have on this part half a millimeter of bigger than the tube.
Oh, over gauge. Okay.
Yeah, that's fine.
Half a millimeter is 1/50 of inch.
Okay. I'll send you some photos of some spiral. Okay. That's very good. It's very good what you're doing there. That's all I have.
Well, thank you then. Thank you.
All right, we'll switch gears and we'll move over to TEC's rig.
Yeah, okay. We have another camera set up on the phone. Good. Yeah, I will not talk so long. I will just hand over to my colleague Ali. Ali, I will take the phone. I think you can explain the best, like the main setup of our.
Yeah, sure.
Yeah, let me just step to the side.
Yeah. All right. So you
there.
can see it. Yeah.
Down there. Okay, I see. Good.
Okay. So this is our setup here. We have, of course, 3 main components, like every drilling rig could. We need rotation, we need weight on bit, we need circulation. So start with our circulation system. We have here our rock sample receiver, which is also our reservoir for our drilling fluid, water. Rock, the water is here. Then our rock sample receiver is connected to a tank system. We have our filter tank, where we filter the cuttings out of the drilling fluid, and then it goes over to a copper tank, a smaller tank in the back. And yeah, then this copper tank is connected to a recharge pump. So we have a 2-pump system. We have a centrifugal recharge pump, and we have a positive displacement high pressure pump. Where both of them we can achieve around 8 bars or 9 liters per minute. So then it's connected, of course, to our release tank, I would say, through an external copper line, and it's then connected directly to our VHA.
You say you have a high pressure pump. What is the pressure?
So with the pre-charge pump, we only get about 2 bars, and then with the additional pressure from the high pressure pump, we get around 8 bars at the end.
Yeah, usually the pump is capable of doing more, but since we have a very big diameter in the drill pipe and the copper tubing, we cannot reach the bar that is labeled on the label. It says 30 to 120 bars, but even if we open the choke fully, it's 8 bars constant.
Okay.
Yeah. Yeah. So our other system
You know, if you have a leak, you never look for a leak with your fingers. Right? If you look for a leak with a high pressure pump, at 8 bar it might not hurt you, but 100 bar it will. It'll saw your finger off.
Yeah.
Never, ever check for a leak with your fingers.
That's a good point. This is also why we made a crucial decision this year to replace our hydraulic system. I mean, last year we were operating with a hydraulic system. Lana later will tell you what we changed, and the safety factor was bigly important.
Okay, good.
So I'll move over to the other two systems just briefly. We have our hoisting system, which we track mounted, electric driven. It's all with the top drive, and this is how we provide weight on fish. And we move most of our important components here, which brings me to our rotation system, which is an electrical self-mounted up drive, and it's connected through a flexible shaft inside a static drill pipe. That's how we move the rotational energy from the motor directly to our drilling bit. So our BHA kind of stays static, which brings me also to the next point, which we have a rotary table also. But we only use this to help us with the steering system, to orientate or calibration or something else, help us with the azimuth.
Yeah, basically we did yesterday we did the measurements. So we used the rotary table to map the output of our magnetometer downhole, and yeah, the rotary table gives us the exact output of our current angle, and you can imagine it like a big table where the magnetometer output is implemented the corresponding angle, and later we can map this and use this during the drilling process to interpret the data that we report.
Yeah. And
with the cylinders connected to the wings on the RSS, do you still use the rotary table?
No. So the rotary table is used only for calibration purposes. We orient the wings in the beginning, and after this, we're purely steering with our RSS system. Although I wouldn't call it an RSS system, since the BHA itself, is static. But I think, Ali, if you don't have anything more to say, this is a good point from Kanan maybe to explain what he did there.
Right. So my part this year was to redesign the BHA, and then from the data we had last year, and to construct a steering mechanism. So I will start with the BHA. Last year we had a fairly longer BHA. This year we have reduced the length of the BHA down to 74 millimeters. So we are down by 50% from last year. We did that to make it easier for the BHA to steer. Another aspect is the outer diameter of the BHA. So when we make it smaller, we can also steer tightly or more easily. So we have reduced this diameter of the BHA also by 5 millimeters from 33 to 28. So right, and we have tried to get the contact points between the wings and the hole a little bit more down, so we have more mechanical advantage when we are pushing on the inner wall of the hole. So we have here we have our a pair of strain gauges to measure our weight in it. This is you come from this side. This is our IMU. Down there we have a magnetometer and an accelerometer to measure our inclination and azimuth. Right. So here now we have a static drill pipe with 3 power cables. This is our new steering mechanism, and I will show you 3D printed model of this BHA to okay. So we have our wings right there, and we have like a wedge under the wing. I think so it's a little bit difficult to get it out. So this is our wedge, right? So and we have like a nose on the wing right there. So this cable is connected to the wedge. So we are when we pull on this string, we can deploy our wings. Exactly, and there we have spring like a sheet metal spring to push the wing down when we retract the wedge. So that's our steering mechanism for this year. Last year we had an hydraulic system. So we
The question.
Yeah.
The wires you're pulling from the surface, is that right?
Yeah, we have a pulley on the surface. Yeah, I will get to the steering unit.
Okay. Maybe few more questions on the steering unit before you move up. How were you able to reduce the length? You said this year you reduced it by quite a bit compared to last year.
BHA length.
The BHA length, sorry, yeah.
Right. Yeah. Okay. So we just redesigned the BHA. So we thought about there was like some places in the BHA that we didn't need, so we can get rid of them. We have reduced the distances between each unit, so the wings are now a little bit shorter, and you see right there it's very close to the place where we have our strain gauges. So last year we had a little bit of more room, more distance between the tip of the wing and the strain gauges, but we don't really need this distance, so we have eliminated the place here for our ball bearings. We have reduced the size of them, and now we have one big ball bearing right there and one smaller. So that's fully sufficient for our weight on bit. The IMU, we got it also smaller thanks to Wolfgang. So right. Exactly. So we just have reduced the distances we don't need. And last year the BHA was made of 2 parts. So we had like a nut between the 2 parts to combine them. Now we have made this BHA of 1 part of aluminum. That saved us a lot of space.
Quick question on the IMU. Do you make your own PCB? Did you change the diagram, or do you use off-the-shelf components for the IMU?
And we make the most of our PCBs in the university. We make them with keypad and milling machine. So you transfer all these PCBs. They are all made at house in the university.
Oh yeah, for the BHA IMU, do you also make your own PCB?
Very small. When it's very small, we can't manufacture it ourselves. So we have printed it. We send it to a service to print it for us because it's very tiny, and we can't manufacture it ourselves.
But the design was made.
But we have designed it ourselves, and I think we have some
not only design, but also SMD,
right.
social.
So this is the new IMU.
So it's only printed by a service, by the external service. We have designed it and we have assembled it. All the parts we have soldered it, and this is now with the resin actually coated to protect it inside the hole while drilling. Right, and those are the cables that are those are the cables here that are going to the PCB on the adapter board. It's like a connection board. But a fun fact for the IMU, actually, we have ordered, I think, 20 empty bases. And from them, we have made, I think, 6. And from that 6, actually just 1 survived. And this was the one which is currently in the BHA. So it was the only one that was capable that we could test in the end. Yeah.
Very nice, very nice. Thank you.
What killed them? When you say they didn't survive, what killed them? Water?
No, so actually, soldering with SMD components, they're so small, and the company gave us a stencil, so we could put the parts on. But even if there's like a tiny, how do you say, kurzschluss, short circuit, some components can break. And if they're broken, it's very difficult to replace them by hand. So I mean, 3 IMUs survived the soldering part, and 2 then died during the resin application on them, because the resin got hot and it shrank a little bit, so it pulled some components out of the PCB. And after it was inside the resin, we had no chance in getting inside it, right?
Right.
No.
Yeah, maybe. So,
How do you have any vibrations, errors with having your electronics on top of the drilling hoisting system?
Yes, for sure. So we can't measure inclination, and we can't measure inclination while drilling. So the accelerometer is very sensitive for vibrations. That's why we have planned our service in a way that we shortly stop the drilling process and then take the measurements. And for the magnetometer, actually, this works perfectly good. So it's like a textbook example when we do the when we take data from the magnetometer. Since we have 2 giant coils generating a hefty magnet field, which is, I think, so 4 to 5 times as strong as the Earth magnetic field. So it gives us very good reference points even when we're in the hole. The strain gauges work okayish. Yeah, we decided to move the actual weight on bit PCB out of the BHA. So this black resin, we have only the strain gauge inside, the cables leave out. I know this is a little bit unsmart to do, since you have a long line until they reach the converter. But anyways, the weight on bit and the hook load matches pretty well. So I think we have differences in between 5 to 10 Newton.
You mentioned that you stopped drilling to take an inclination survey. Do you do that regularly, and in what interval?
Yeah, so this would be probably already the algorithm part. Yeah, so in the autonomous algorithm, it works basically like this. In the initiation part, we interpolate our trajectory. We split the trajectory into equally large space survey stations. We can decide how many. So we will probably head for something between 10 and 20 for 60 centimeters. And then we would have 20 measuring points in order to build our actual trajectory.
Okay. Do you calculate vertical depth?
Yes, we do. We're not calculating it, we're measuring actually by a potentiometer. I mean, Ali, if you go around, you can show them the digital digital display. We're calculating, we're measuring the position from where the robot starts. During the initiation process, we have a rock zero approach where we Tara the depth, and yeah, basically we have one starting depth and one rock start depth that we log.
What's the difference between measured depth and true vertical depth?
True vertical depth is how deep are you in the rock. The measured depth would actually be our drill pipe length, because when we are deviating, hopefully we will, the true vertical depth is going to be smaller than the measured depth, since we have an inclination.
So how do you calculate what method do you use to calculate vertical depth?
We use, it's a simple method till now. We use a tangential method, I think it's called. So we're interpolating the parts in between the surface and the line. And this is our method to calculate the measured depth. And
okay.
Sorry, I think I mixed something up. True vertical depth, right?
I'll ask Tim and Mark to talk to you about that offline to get a better understanding of that. But we don't need to do it right now.
All right. I think we'll take over and yeah, tell you of the steering.
Ali, you want to move that?
Hey, I have one more question on the BHA. So your bit is your first point of contact, then you have your wings or the pad. That's the second point. Where's the third point is at the top of the BHA? Is that right?
The third point is the stabilizer. We have three points on the stabilizer, so this is our third contact point.
So when you said you reduce the length of the BHA, which means you now have a higher dogleg capability?
A higher what?
Higher build rate capability, right?
Yeah. Yeah.
Okay. Okay.
So those are the cables from the IMU and the strain gauges, and then we have three Bowden cables. Those go to the steering unit. So those are the steel cables inside the Bowden cables. They are pulled by pulley, which is driven by a DC motor, and we have on the other side a rotary encoder to measure the position, and in combination we have like a servo motor, so we can exactly deploy and retract the wedges on the DHA. Exactly. So I think I will. Oh, right. We want to show you how the wings are deployed and retracted. My colleague is gonna send a command to deploy the wings.
Take pictures of the robot. Maybe just hold the camera from the outside.
Yeah. So
yeah, good. So no.
Actually, so this is it was this the maximal?
No, it's 50%.
This was just 50% of our maximal.
Which wing
is that? It's wing. Wing two.
Wing two. Okay. Then wing two to
80%.
Exactly.
So now we can deploy it. Right. So
Do you
this
have
is one-
interference problem with the magnetometers there?
You have to repeat that, please.
Do you have problem of interference with the magnetometers of the sensors?
The magnet, I don't think so.
Magnetic interference.
All our parts are made of aluminum. So they are not, we don't have interference with the magnetometer.
So in every survey, you check for the interference then to quality control of the survey, right?
No, so actually how we interpret the measured data is we in the beginning when we calibrate the sensors, we map a certain range of angles. So we basically look for the output of the sensor and give it the current angle. So for the azimuth, we have rotated the DHA by 1 degree and measured or took the data, and then we knew, okay, this data point corresponds to this angle. The same for the inclination. This is some. I mean, you could already tell it's machine learning, but it's just interpolating the data in between two angles as a line. So even if we have slight deviations in the measured data during the drilling process, it will still be somewhat accurate. So obviously it's not precise, not extremely precise, but for the azimuth, I mean, we had measured outside and we had do the calibration and measured in the hole, and we had like deviation to 4 to 5 degrees. Yeah. For the inclination, it's a little bit harder because the accelerometer is very sensible. So there we had close 7 to 8 degrees in deviation from the actual implication.
What is
Okay. But you have any way to do a quality control of the survey in case that, for example, somebody came with a watch or whatever that have interference? Do you have any way to realize that there is a problem in the survey?
So basically, we have a way. When we do a survey, the drilling process has a feedback loop that asks the IMU frequently to post a statement. So we ask the IMU, so we request the data, and if the IMU is not responding, we ask it again until it sends it, until an error state is reached, and from there, most likely the IMU has given up. And our plan B for today would then be to proceed with the drilling, and assuming that our planned survey point is our current survey point, so that we can still have a somewhat decent direction that we can drill directional. Let's say it like this.
Did you try to use MEP gyros as a sensor?
No. We didn't use gyros. I mean, we can think of implementing it, but the simpler approach for us was going with one accelerometer and one magnetometer.
Thank you.
Are you orienting towards magnetic north, or how are you getting a reference for your azimuth measurements to go off of?
So our magnetic north is pointing actually in this direction, since we're generating our own magnetic field, and we subtract from that 90 degrees to get our actual 0-degree position, and this would also be the line in which the first patch should align. So we're doing this with a laser calibration instrument, and from there the position of the BHA or downhole tool is fixed, and there we start running.
Oh, very cool. So your sandstone there is like oriented directly to your own magnetic north.
Right.
Very cool. Okay.
Yeah, I mean, we can, I don't know, Kanan, have you something to add? Otherwise, I would go through the GUI and a little bit of the algorithm real quick.
I think that was it.
Yeah.
We actually understood.
Okay. Okay. Here's perfect. Okay, let's maybe have a speech. Oh yeah, of course. Yeah. Since last year, we had a little bit of a problem with our old drill bit. Nikon Drilling was very nice to help us to design a new drill bit. So this was actually also manufactured by them. The design was made by. So I designed it together with two drilling engineers from Nikon. They helped us very much. They told us all about the specifications that a drill bit should have and what we should use. And yeah, just for mentioning some things, the gauge side is actually not 90 degrees, but a little bit tilted, just to reduce friction on the gauge side. And we also implemented a cone angle, but it's a very slight cone angle. This should help the drill bit to somewhat stabilize itself. And last year's drill bit had a round shape, so the cutting velocity as you move to the center of the drill bit was becoming zero. So we didn't really have a drill bit. We had a spinner, so the BHA was actually tangling on the rock like this. But with this bit, we had a major improvement of the drill string stability and also in the rate of penetration. So during an accidental test, we reached, I think it was 1.7 millimeters per second. Yeah.
Wow.
Back to the pads. You're independently actuating each one, right?
Right. Yeah.
How frequently do you actuate it when you're steering?
So we give the command to deploy a specific wing once every survey station. So then we drill at a constant distance till the second survey station, and then we get the data from the IMU. Also we get our inclination and azimuth. Then we calculate our new steering vector, in which direction we have to steer, and then we give the wings new commands to how much they should deploy and which one to deploy.
And between survey stations, you hold the same pad actuation. Is that right?
Yeah.
Okay.
So that they deploy gradually, but once they reach their position goal, they stay at this position till the next survey station.
Okay.
You're not using Bluetooth this year, are you?
We are not using what?
Bluetooth.
Bluetooth. So
No.
are you measuring the voltage off of the card inside the BHA? Are you getting volts, millivolts, or current, or what are you actually measuring when you measure one of these angles? What's going through that wire?
Through the wire, we have a 5-volt supply and our CAN-bus line. So we have 4 wires inside, 5-volt plus, 5-volt minus, CAN low, CAN high. And the IMU itself has the CAN transceiver on it. So the accelerometer gives us output in milligauge. There is already a library together with the sensor, so it converts them to milligauge. And for the magnetometer, I think I'm not quite sure, but the output was in machine units, but I will have to look this up right now.
Okay. All right.
So is it a digital sensor or an analog one?
Good question. So the accelerometer is a analog, I guess. But sorry, MEMS sensor. Yeah. And a magnetometer, also a MEMS sensor. Okay.
I see. So, but to communicate the measurements, are you using a digital bus of some kind, or just taking raw voltages and converting them to the actual values?
I didn't understand the question.
Are you using a digital bus or a digital communication, like I2 or CAN bus, or are you only reading output voltages?
CAN bus. So all modules that you see on the rig are connected via CAN bus, and it's
including the downhole sensor, right?
Sorry?
Including the downhole sensor?
Including the downhole sensor, yes.
You have a CAN bus in the downhole sensor, or is it the raw voltage coming off of the board?
No, we have a CAN transceiver inside or top of the IMU, which basically sends the CAN messages already from downhole.
Okay, so the IMU is sending a digital signal. Okay, that's good to know.
Got it. Thanks.
So we don't have to have a long talk about interference.
I swear interference was one of the biggest problems that we had. Like the CAN bus was packed full with noise, and we had to come up with very fancy filters to somewhat keep the noise out of the CAN bus. In the end, we decided to split all voltage supplies from the main cabinet, so that the motor is having his own voltage supply. The 5 volts are independent, and also the 24 volts. And we ended up with what is Netzteil called in English? Yeah, with 4 power supplies inside of our main cabinet. They're all below 50 volts, so it's a safe. It's German standards. It's Kleinspannung. They're safe to operate. So nothing that you see here can be deadly for when touched for milliseconds. But even if there's some wire hanging out and you touch it, we have FE switches that will cut off the power supply, and we have actually 2 emergency switches. One is over here for besides the rig, and one is right. It's on the table right here, basically where the driller console is. So that the driller can also, if he notices something, just press the button. And this one here is it's really cutting the power supply. That one on the table is just stopping all modules. So we send a signal to all modules. Yeah, and of course to the relay module. So the relay module, it's also a module, but it's responsible to control the relays that activate the power supply. So basically, the relay module would then be told to cut off the power supply. But the hard cutoff is the red switch over there. Yeah. Good. If there are no questions for this part, I would head over to the displays. And I and Farouk are going to tell you a little bit about control and what we have for visualization going. Yeah, Farouk, do you want maybe to start with the GUI?
Yeah, of course. So we have our GUI, graphical user interface. Every data that comes from the sensor, from the machine, are being worked on displayed here right now. Now the server on. That's why we are becoming this slide. Our server is accessible from any point around the world. Also the GUI and the control unit here. Just have to download it and make it running. We also have to write our graphs, as all data are being displayed right now because there's no movements, there's no data. But we like our hook load with depths, RPM, torque, pressure, hook load, weight on bed, rate of penetration, etc.
And next to the visual displays, we also have a logger running in the background. So since our architecture is decentralized, we can basically log in with as many devices as we want. So we decided to split most of the tasks into different clients. So we also have a logging client, which is connected to the machine and logging all commands, data, everything that has a visit through the CAN bus is getting locked in there. But yeah, some of them are not very useful to lock. Some of them are constant or any kind of commands that we put in. But later for the Auswertung, what do we say? Yeah, for the data processing, it's very useful to see when somebody did something. So yeah, you can also mention what we have going over there with the lights.
Yeah. Now, our modules are being displayed right now, and the modules are turned on, then they're turned red. When it's off, it's blue.
So basically, also when we lose a module during the
drilling, we get the signal immediately that something wrong.
For the IMU, we have switched it off. Since the IMU should be every time ready to just give out the data that it reports. And I won't tell, it's a little bit fragile. I mean, yesterday we drilled with it through the hole. We couldn't resist. We wanted to try the steering system. Yesterday was the first time we actually operated the wings during drilling. And the IMU survived, but we figured that it wasn't well responding on the constant pinging to the module. So we left it out. The drill string module is, oh, okay. Yeah, yes. Yeah, the drill string module is not there. We have not implemented it yet. Actually, it was planned to have the IMU mounted also on a drill string for drill string sensors, since the accelerometer can also be used for measuring vibration. And I think it had also capability of measuring temperature, right? Yeah. So, but yeah, we have none left, so we couldn't do this. Yeah, maybe just having. Yes, the dashboard. Yeah, maybe just heading to the engineering interface, as I call it. It looked like this.
Question. One question.
Yes.
If your pads don't deploy as you expected, what kind of feedback do you get? Is there something that's measuring the position of the pad, or you rely on the next survey measurement to say, I'm not getting the steering I need, so something is wrong with the pads?
No, we have actually two ways in order to know if the pad is activated or not. Kanan, I think you have done it, you know, right?
So we have the rotary encoders on the pulleys on the steering unit. So we can exactly measure the position of each wedge separately. Right.
And the motor.
Okay,
right.
That's pretty neat. Okay.
On Bowden cable, we have a load cell, so we can determine also if we are in contact with the inside wall of the hole or not. So when we contact the hole, we see that then we measure the force with the load cell, and while steering we are pulling the cables with a constant force of 350 Newton. Right.
Okay, that's pretty neat. Okay, thanks.
Yeah, we left on the engineering interface, so we'll just go quickly through it. We have another bar for pinging the modules manually to know what's going on. Basically, what we did for the control algorithm for the whole machine is we have each module that is mounted on the rig has basically a digital component to it. So each module can be actuated and has its own commands that we can use from here or from the control algorithm. This panel is used to do the basic things that you need. Driving the Z-axis, you can drive it in millimeter and adjust the speed in millimeters per minute. You can drive the rotary table to how many degrees you want. And yeah, you can implement your set point. You can also decide when you want to switch to the next survey. So you can actually, I'm not sure if it's visible. Let's just turn it like this. Maybe it's better.
Oh yeah.
Yeah, good. So you can also, during the drilling process, you can decide if you want to switch to a next survey. So if you see you are on track and you want to maybe make the drilling process faster, you can just skip one survey. This is possible. Also, as we drill deeper, the VHI drills become more stable, so you can increase your weight on bit set point. This is actually a wrong label right here because we decided not to use the weight on bit as a set point for PI controller, since the strain gauges, due to a lot of heat generation, since we are using 3000 RPM, are drifting hardly, so it's not reliable. But one reliable source was the current from the motor. So we are actually actuating the current from the motor, the amps. And the correlation is, I think, 1.5. So 10 ampere would mean 5 Newton meters. So yeah, this would basically then be our set point. And if we decide to increase it, we can also do this while drilling. Yeah, actually, while the autonomous algorithm is drilling. Down here, you can see another adjusting boxes. It's a steering control, so you can actually actuate the wings manually. And yeah, on the left for the motor control, set the RPM, turn the motor on. And maybe the most important box for today, the set target point box. They will implement the target points and they will be hopefully hit. Yeah. When using this for the autonomous algorithm, you're basically only using this part over here, which is the state machine by itself, the motor control box in order to set the first values that you want to use, the target points, and your weight on bit set. The main state box, which I said is used for controlling the state machine, also activates. So when operated in the right order, the main state box will also activate a commander, which is basically the autonomous part of our robot. So the commander, I call it like this. It's basically also a state machine, and the only thing it does is it's not changing the states, but it tells the machine what to do. Yeah. So the machine basically is a loop running through 5 states: drilling, initiation, steering, park, and survey. And the commander checks for certain conditions around what is happening on the rig and decides then what state to use. And yeah, we have tested it a lot of times out of hole, but today will be the first time that we will use this algorithm to actually drill through the hole autonomously. And yeah, I think this will be enough. I could go into more detail if there are still questions, but yeah.
We can deal with some questions while you're drilling as well, right?
For sure.
Yeah. And as when we get it, once you start drilling, we'll go ahead and start drilling in a little while. But I'd like for you to explain a little bit more about how you go from the targets that we give you to creating a well plan, and then in the GUI, I can't see where you show plan versus actual.
Yeah, plan versus actual is actually not implemented right now in the GUI. I have it here in a MLab script represented. So we basically are going to copy the data that we're getting out of the machine, and we will put it into the algorithm, and then we can have a view of the planned trajectory to the current trajectory. So this is just a line that I have put in. This would basically be the output of our interpolated trajectory. So if you give us four target points or 3, we would interpolate a trajectory through it with the derivative on the contact points should be constant, so it should be a smooth line. And yeah, in order to detect our actual trajectory, we would use the tangential method as stated before. So out of the azimuth and the inclination, we would construct a vector that we will add onto the previous vector. So our first vector will hopefully be straight, and from there the algorithm would then use inclination and azimuth to construct the next vector in order to have the so-called BHA vector. So this maybe looks a little bit off, but it will make sense when I turn it this way. So the BHA is actually looking in this direction. So the plane that you see here is the tool face plane, and when looked from above, this is also how we then use the steer. So how we calculate the steering force. When we look from above, we would take the next survey point S4 and project it onto the plane to get basically the target vector projection in the tool face plane. So this vector would then have an angle and a magnitude, and we are only using the angle of this vector for calculating our pet forces. So the target vector would be rotated by 180 degrees to get our force vector, and from there we split the vector apart in, we show it over here, in, okay, I choose a bad example, maybe I can zoom a little bit, hopefully. So, okay, matplotlib is not so nice sometimes, but you can see what is happening here, right? We want to steer to that point, to S4, and if we flip it, the force vector would be somewhat around 45 degrees. So this would mean that the pads A, the blue small line, and the pads B, the orange line, would have to be activated by that kind of percentage in order to steer into this direction. So as I said, the magnitude is neglected here. We are just using the ratio from them. So we assign the target vector a magnitude of 1 and see what kind of ratio is between the two pads involved in the steering process, since we are only using 2 pads at a time to steer. And this is then published onto the broker and picked up by the module. And on the module later it is converted with force conversion. And we are using as much force as we are capable of doing without breaking anything.
Okay, we're kind of running out of time, but if any judges have a question, now is the time to close it out. Okay. Olympus, I don't have your email, so I sent the coordinates to Martin. Okay. So if you go over and talk with Martin, he should have the coordinates and he can share them with you.
Okay, fine.
I can just settle.
Okay. How long do you think it'll take to enter the coordinates?
By 40 minutes? It's okay? 40 minutes? More than or 30 minutes?
More than 30 minutes.
More than 30 minutes? Okay, and so we would need 40 minutes. We would do the pilot hole and then we would start. Maybe earlier. So as soon as we finish, we would then tell you.
Okay, well we'll take a 30-minute break. We'll stop the recording. We'll take a 30-minute break, and meet back at I guess it'll be a quarter, 15 minutes before the hour.
Okay.
And we'll see what status you're in at that point. Okay. All right.